Haley, are you hip? Are you happening? Are you now? Hip happening now. What's back bling?
What's what?
Back bling.
It's from a game for
Haley, I thought you were hip. I thought you were happening. I thought you were now. You don't know what back bling is?
No, I shouldn't.
I don't know what it is either. So. Hmm. 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 All right, ladies and gentlemen. Well, Haley, here's the worst part is you're going to be called out on YouTube because I just recorded that conversation and people are going to be like, Haley's not hip, Haley's not happening, Haley's not now. It's okay? All right, good. Wow, it's a lot quieter in here today. I don't know why. Okay, ladies and gentlemen. So today we're going to talk about the lab that we did yesterday. Now, okay, I could do this. All right, so I don't have a question of the day for you. Your test is scheduled for next week, Thursday, ladies and gentlemen. And the good news is because we're here today, we don't have to move that. Okay? So we're still shooting for that, ladies and gentlemen. But we do have a lot of work to get done next week in a couple days. But you know what? I have great confidence in you that we can make it. Okay? Great confidence in you that we can make it. So take out your lab, ladies and gentlemen, and let's take a look at the lab. Okay? Let's take a look at the lab. Now, I did mess up a little bit here, ladies and gentlemen, in that I changed the questions for next year. So you're going to have to help me here. All right. First of all, ladies and gentlemen, in this section of your lab, if you do not have at least 3 out of these 4 boxes filled, you will not get your point for this section of the lab up here. That's 2 different points that you could earn. So if you don't have at least 3 observations of magnesium ribbon and 3 observations of hydrochloric acid, you better come up with something. Then the same is true for the reaction here, ladies and gentlemen. Okay? You need to come up with at least 3 here. When you get to this table, ladies and gentlemen, the biggest error that people will make, you get 1 point for each sample. The biggest mistake people make here is they do not include units. I will not give you credit if units are not included. If you're giving me just numbers, you're not actually telling me what the room air pressure was. Okay? So make sure you're putting units on all of these. And oh my God, ladies and gentlemen, I don't know if it was this class or my other, but I went and I looked at some people's information here. And I was absolutely appalled. Appalled, ladies and gentlemen. Appalled by the fact that you can't take a measurement with a digital instrument. Can you believe that some people, for the mass of magnesium, put down 40-some grams? 40-some grams would be the mass of this block, ladies and gentlemen. You had a little strip of magnesium ribbon. And our balances read to what place, ladies and gentlemen? Thousands. 0.000. I don't know how it read 42 without at least 3 zeros after it. But when I looked, ladies and gentlemen, there were some people who had a mass down of 42 grams. That doesn't seem possible to me. Questions, ladies and gentlemen. I hope that wasn't you. What unit or what place should our temperature of water have been to? Tenths. The digital thermometer reads to the tenths. The volume of the gas collected, ladies and gentlemen, I agree with you when you looked at the marks on that instrument and you read to the ones place. There was 42, 43, 44, 45. All of them were there, ladies and gentlemen. But I looked a little closer. I saw some lines between 40 and 41. Now, did you see enough lines that the tens place was there? Because if you did see enough lines that the tens place was there, what place should your measurement have been to? If the instrument's reading in the tens, your measurement should be in the hundredths, ladies and gentlemen. Why? Otherwise, you're losing a sig fig. Don't want to lose a sig fig, ladies and gentlemen. You lose sig figs, that's a bad thing. So hopefully, ladies and gentlemen, your volumes are to the right place. Now, our last number, the partial pressure of water vapor. How many places beyond the decimal was that? 4? 4? You're right. 1 before, 4 after. Ooh, look, here's one where there's only 3. I wonder why that is. Here's one where there's only 3. I wonder why that is. By the way, this is the table that I gave you, correct, ladies and gentlemen? Now, I realize that you guys are all great language arts people. And you realize that if you use a resource, you need to do what with it? Cite it. Look at the citation on the bottom of that. Can anybody read it?
Handbook of Chemistry and Physics, 64th edition.
Ladies and gentlemen, I have the Chemistry of Handbook and Physics right here, 62nd edition. This was from 1981 and 82.
The Chemistry of Handbook and Physics?
The Handbook of Chemistry and Physics. What part of the sentence did you
said
not understand?
You said the Chemistry of Handbook and Physics.
Anyway, ladies and gentlemen, this is the 62nd edition. That information happens to be from the 64th. What year was it again, Dante?
83 to 84.
83 to 84. Are you telling me that information is 40 years old and still good? 40 years old and those vapor pressures have not changed? No, they don't. They're a target. They're a known value. Why would they change? Does the boiling point of water change over the next 40 years?
No.
No. Does the density change? No. So everybody thinks, oh my gosh, I'll go to the internet and get the latest and greatest information. The information you got yesterday was 40 years old, and guess what? It was still darn good. Why? Old things are awesome, ladies and gentlemen. Old things are awesome. Good. Now we can move on. Questions? Okay. Now, again, you're going to have to help me out because I realized that after I did the lab for you, some of my questions, how can I say this nicely, sucked? So I changed a few of them. Doesn't mean we can't do them. Most of my questions stayed the same. A few of the calculations changed. And just how I worded them. So you may have to help me out here, ladies and gentlemen. What does our first calculation say? Yes, thank you. Awesome. Excellent.
Assuming all of the magnesium gets used up in the experiment, how many moles of hydrogen gas should have been produced?
Okay, good. What that basically means is this, ladies and gentlemen. Did I tell you about the preview? The preview of Unit 7?
Don't think so.
Okay, good. I will do that right now, ladies and gentlemen. This, ladies and gentlemen, is the balanced equation for our reaction that happened right there. Right there. Right? Okay. What is the coefficient in front of magnesium? The big number that's out in front. 1. Okay? That means 1 mole of magnesium. Okay? What is the big number that's out in front of the hydrogen gas here? 1. What that means, ladies and gentlemen, is that magnesium and hydrogen gas are in a 1-to-1 relationship in this equation. A 1-to-1. Meaning, for every 1 mole of magnesium that we begin with, we will create 1 mole of hydrogen gas. If we start out with a 1/2 mole of magnesium, how much hydrogen gas are we going to create? A 1/2 mole. So that is the basis for where we begin this experiment. We began it by finding the mass of your magnesium, assuming you didn't write down 42 when it was probably supposed to be 0.042. Okay? So anyway, ladies and gentlemen, we need to take and convert that mass here into moles. What do we use to convert mass to moles?
Formula mass?
Formula mass. Good. What's the formula for magnesium here, Anthony? Don't even go look at that. at the balanced equation I just showed you. What's the formula for magnesium?
MgS.
What's the formula?
What do you mean, Mr. Brand?
I mean, what's the formula?
Like the whole thing?
Yeah.
MgS plus.
No, stop. Just the magnesium.
Mg.
Good, thanks. I didn't need the S.
Oh.
We all know that it's solid, but thank you. I just wanted Mg. So what's the formula mass for magnesium, Andy? Now, when you take a very small number, like 0.042 grams, and divide it by 24 point something, 31, right? What kind of number are you going to get? A small decimal. Don't be shocked by a small decimal, okay? Don't be shocked by a small decimal. Good. Any questions on calculation number 1? Yes, no, maybe so? Okay, what does number 2 say? Because I know it doesn't say the same thing it says up here.
What is the value for the vapor pressure of water in this air?
Where did you find that? Where do you already have that in the lab?
Partial pressure.
At the bottom of your final table, the last piece of information was the vapor pressure of water at that temperature, right? For this question, all you literally need to do is copy that number down again and put a unit with it. Questions? Okay, what's the third question? Or third calculation? Okay, how do we find the pressure of just the hydrogen gas, ladies and gentlemen? How do we find the pressure of just the hydrogen gas? Okay, well, what it leads to, ladies and gentlemen, is this. Not all this crap, okay? It leads to this. There is a mixture of two gases in that container. What are they? Bless you. That's not a gas, by the way.
Hydrogen gas and water vapor.
Okay, so what it really means, ladies and gentlemen, is the total pressure inside that gas collecting tube has to be equal to the pressure of the hydrogen gas plus the pressure of the water vapor. Okay? Does that kind of make sense? If you have two gases in a container, the pressure of the gases in the container should be the pressure of each gas added together, right? Because what is pressure? Does the container care what kind of particle is hitting it? No. But if you have two gases in a container, one gas is going to hit the wall every so often, the other gas is going to hit the wall every so often, correct? And if you add that up, that's what the total pressure would be. How often they hit the walls of the container together. That's where this comes from, okay? Are we clear on that? So we should have this number. That was the one we got as the room pressure, right? This is the one this is the one you looked up in the book, right? So how do we get this one? Good. Show me how you did it. Do that, okay? Do that, okay? Questions? We're good there?
This is for the third question, right?
Yes, it's actually the third question, not the second question. I'm sorry about the confusion on that. Okay, third question. Okay. Questions? By the way, what can you tell me is the same about both of these two gases?
They both have hydrogen.
Okay, but yeah, I'm sorry, my bad. What can you tell me is the same about the conditions of these two gases?
Under the same temperature.
Well, if they're in the same container, went through the same water, they should be at the same temperature, correct? What else is the same? You can almost hear the water dripping down the sink.
The volume.
Their volume. Their volume is the same, correct? So if temperature is the same and volume is the same, but pressure is different, right? What else has to be different? The amount of each gas, correct? the amount of each gas must be different, right? Okay? So, what determines the pressure of each gas?
The amount of substance.
The amount of each gas. They have to be in a relationship here, correct? What kind of relationship are they in? By the way, ladies and gentlemen, what I'm going through right now is really going to help you on your test.
A direct relationship.
Why?
Because one goes down and the other goes down.
Okay, very good. So, ladies and gentlemen, I want to go back here for a second. This is, we don't need this for the lab right now, but I want to point this out. What are our four variables and where do they go in our formulas? What's one?
Amount of gas.
Where does that go in our formulas?
At the bottom.
Okay, what else?
Temperature.
Where does that go? I heard top and bottom. Which one? Temperature is on the bottom. What else?
Control pressure.
Where's pressure go?
Top.
Okay.
Bottom.
Volume goes where?
Top.
Okay. Now, these two right there, pressure and volume. What kind of relationship is there always between pressure and volume? Inverse. Why?
The pressure goes up while it goes down.
Okay, and if we look at them mathematically, what are we doing to them? We're multiplying. Okay, good. So now, what about these two? Pressure and temperature. What kind of relationship are they in? They are in a direct. Why? Because you're dividing them. Okay, good enough. Fair enough. I'll take that. What about volume and temperature? What kind of relationship are they in? They are also in a direct. Correct? Why? Okay, good. You're also dividing them. Running out of colors here, ladies and gentlemen. What about volume and amount of gas? Ooh, I don't have a yellow pen. Guess we're going to have to make do. They are in a direct relationship, correct? Okay, why?
Because you're dividing.
Okay, good. Now, what color have I got left? Ooh, I guess I'm going with black. What would pressure and N be in? Michaela, what'd you say? Why?
Because they're being divided.
Because they're being divided. Now, there is no gas law for pressure and amount of gas. There just isn't one. Okay? Boyle, Charles, Gay-Lussac did their work. Avogadro did his. And they're like, well, there's no sense in going into more gas laws. Because we've already proven everything that there can be. It's not a gas law, but pressure and amount of gas have to be in a direct relationship because they are what?
Divided.
They're divided. So what we were just talking about, if we have these two pressures that are making up the total pressure, it's because we have two amounts of gas making up the total amount of gas, right? And if one gas is less than the other, its pressure is going to be less than the other. What if you have an exact equal amount of both gases? What's their pressure going to be? Each one. The same, or half of the total, right? So if you have a total pressure and it's made up of two equal amounts of gases, they would have equal pressures, correct? What if one was twice as much as the other? What if there were twice as much of one gas as the other? What would that mean for pressure?
Because there's twice.
There would be twice as much from the one gas as there is from the other, correct? So let's say 900 total, 600 would come from one gas, 300 would come from the other, correct? There is a relationship there. Now, we've never gone through it, right? But there is a relationship between these two variables, correct? What would be the relationship between these two? Why? because you have to multiply them. If we were to ever look at the relationship between temperature and amount of gas, holding pressure and volume constant, this is an inverse relationship, which means if you add more gas to a container, what has to happen to the temperature?
Go down.
Has to go down. Has to go down.
Oh, because the amount's going up.
Correct. Correct. They're in an inverse relationship. And again, that is applying the gas laws. We haven't, we didn't talk about, oh, there's Mr. Brand's law, which relates volume and... Wait.
Why don't you just make your own?
I should. That's a great idea, Andy. We're going to start talking about Brand's law.
What if I say-
We're going to relate temperature and amount of gas. Yes. I have a way to fame and fortune yet, ladies and gentlemen. Okay? No, we're not going to do that. Okay? But the point is, there are all kinds of relationships here, correct? Any questions? Good, because you still have blank looks on your face like, oh my God, I can't wait to get out of here today. Anyway, okay. All right, let's go back to what we were talking about then. Okay, so this question has messed people up today. This is question 4 for you. Same exact question, but it's question 4 for you. And it says, knowing the temperature, pressure, and volume of the hydrogen gas, how many moles of hydrogen gas were produced in the reaction? What are we going to use to solve this?
Temperature, pressure, and volume.
But what formula?
PV, NRT.
PV equals nRT. Ideal gas law, probably the easiest thing to use. You know what people have done today, though? Shenza, one of my star students in the last class, calls me over and says, Mr. Brand, I think my calculation's wrong here. And I look at it and said, of course it's wrong, Shenza. Do you know what he didn't do? Give you a hint. Temperature.
Convert
He didn't
Kelvin.
convert.
He didn't convert temperature to Kelvin. That just broke my heart, ladies and gentlemen. Broke my heart. But then I looked further.
What's his name?
Shenza.
Oh, he's really good at
I looked further and I'm like, Shenza, you messed up number 2 on the same problem. Because he never converted temperature into Kelvin. Now, he did use only the pressure of the hydrogen gas. We don't want the total pressure here. Why?
And do it just want the hydrogen.
We only want the pressure of the hydrogen gas. He did that. He said, Mr. Brand, I only used the pressure of the hydrogen gas from question, I think, number 3 above or 2. Which one was it?
the 3.
3. Only use the pressure of the hydrogen gas. But you know what he did wrong again?
Again, he didn't convert it.
He didn't convert what?
Calcium to Kelvin.
No, we already talked about that. That was my first major disappointment with him. You know what the other thing he didn't convert?
Standard
Grams to moles.
It doesn't matter. We're solving for moles here. We're solving for moles here. You know what he didn't convert? He used the volume in what unit?
Milliliters.
What's the problem with that?
22.4 liters.
The R value uses volume in what unit?
Liters.
Liters. He's like, Mr. Brand, I got a number that's about 1,000 times too big. Yeah! Because you didn't take milliliters and convert it into liters, which would have made the number 1,000 times smaller. Don't make that mistake, ladies and gentlemen. Don't make the Shenza. Don't make the Shenza. In this problem, remember, only the pressure of the hydrogen gas and your volume has to be in liters. This has to be in Kelvin. Do the calculation. Let's go get it done. Come on. Come on, come on, come on.
Guess what, Mr. Brand?
Chicken butt.
Where's her name?
Where's her name?
Where's I forgot her name. We're gonna lab together.
Kaylee?
Kaylee.
I'm glad you know her name.
I do know her. I didn't know her name. I just
Yeah, whatever.
Okay.
Whatever, Rudy.
I don't have the information because my computer died and there was no charging block, so we took the
Oh my
other one.
God. And we ran out of paper and pencils, and there was no way to write it down. Well, now you're in trouble because you got to figure out how you're going to get that by the end of the day to turn it in on time.
I'll message
Okay. You do that ghosty chap thing or that Rick Rock or whatever you young people do nowadays.
You need some
Use
time?
face chat.
Face chat.
Yeah, whatever. Go ahead and send out a twit.
Yeah.
Yeah, find out. Good. Take care of that.
I'll do that.
Okay, good. Questions?
How do you spell her name?
Hername. Any other questions, ladies and gentlemen? Keily. Okay, now you've never done this calculation before. You're going to do it right now, ladies and gentlemen. We are going to find something called percent error. Basically, we know how much you should have gotten. We know how much you got. Let's compare the two. Now, the way we find percent error is it is experimental minus accepted over accepted. Okay? Now, I know that sounds crazy and it sounds confusing, but it's actually quite simple. The experimental value is what you got in number 4. When you did the experiment, you collected a certain amount of hydrogen gas. You got the moles of it in number 4, correct? Good? Yes, awesome. Number 1 was how many moles you were supposed to get. Because for every mole of magnesium, you were supposed to get a mole of hydrogen. So number 1 should have determined how much you got in number 4. Calculation 1. So we are going to take the number that you got in calculation 4 minus the number that you got in calculation 1. And then divide them by calculation 1. That's the formula. Now, the one thing you have to be careful of is when you do this part up here, ladies and gentlemen, in your calculator, put it in parentheses. Make sure you get an answer for doing the subtraction first before you divide by this. Now, what kind of number should this be? What would we want our percent error to be? Like 99% error or like 1% error? We want it to be as small a number as possible. But to be a percentage, again, remember we have to take it times 100. Your units will cancel out here. Moles and moles will cancel. The unit that you will be left with is percentage. So when you take your number 4 calculation minus 1, then divide it by 1, you should get a very small number when you multiply it by 100. Now, I don't care if the number is positive or negative, ladies and gentlemen. That doesn't matter, but you should get a small number. Anyone have questions on that?
Calculation number 4 was...
What you just did, the PV equals nRT. You found the moles of hydrogen gas there. Calculation number 1 was you found the moles of magnesium, which are equal to the moles of hydrogen gas, or should have been. Questions? Okay. Let's go through these questions real quick. I'm not going to answer them for you, but I will point things out for you. And I did not change these, so we're good there. And then you can have a few minutes to finish up your lab. Call me over if you need to. Why was it necessary to equalize the water level inside and outside the gas collecting tube? This was when you took it and you put it into the graduated cylinder and you moved it up and down. Now, I don't want you to try to answer this, not to me, not out loud to the class. But there was a reason we did that. There was a reason we put it in there. And it was to measure something that it was the only way we could measure it for the gas inside the tube. What did this allow us to find out about the gas inside there? That's what your answer needs to be here. Okay? Question number 2. This is the same question as in yours. I just asked for a little bit more clarification. What was the total pressure of the gas collected in the tube? I don't want the number. I want what the total pressure was made up of. What things made up the total pressure inside the tube? Okay? What things made up the total pressure inside the tube? And then finally, ladies and gentlemen, questions 3 and 4 sound the same, so let me clarify for you. What is the value for the vapor pressure of water in this experiment based on? Don't tell me what the number you got was. Tell me what we used when we looked at that reference sheet to get the number. What was it based on? In this reference sheet, what determined which of these numbers you picked? That's the question that I'm asking you there. And then finally, how was the value for vapor pressure in this experiment found? Where did we get that table from? You need to tell me what we did to get those numbers. Okay? Questions? You got 5 minutes, ladies and gentlemen. If you need my help, call me over. Otherwise, get this done and get this turned in. Everybody except for Ruby, who doesn't have any of her numbers because she didn't get them from her partner the other day. Now she sits there without being able to do it. Yeah. Monday's going to be too late. It'll be late by then.
Okay.
Hold on, I got to put Ruby's phone away for her. I'm coming, Haley. Just relax. I move slow. That's what can I do for you?
I don't know. This don't make sense to me. I was one of those people.
Well, you were not the only one who did that. But I think what you're going to find is the number was probably zero. No, that's what I think. When you do your calculations, I think that's going to work out the best. Now, again, the milliliter. I don't think the instrument read to the inverse place.
Okay, so that's why I had it.
Okay, so now go do your calculation based on those numbers. Please remember. Okay.
So that still be like so.
Well, remember that's now going to add another zero in front here, which is going to add a zero in front there,
Just add a zero where?
and there in front of the one. Now double check because
I will double check.
do that real quick. Do that real quick. 0.046 divided by 3.13. No.
I did it wrong.
Stop moving it around.
I did it wrong because it's mine, so it's
But-
rounded.
Okay, take out that extra zero we put in because I don't know if you copied the number wrong originally or what, but that was what it was. Yeah, okay, good.
Mine was wrong. And then this, you have to convert it correct. So you can know what it's-
Correct. Which, now, if we divide that number by 1,000, we're gonna divide this number by 1,000. I think you're finding
This
that you're
final
not
answer?
that far off.
Okay, let's stay right here, Mr. Brown.
Do you have another question?
Yes, actually. I don't understand these two. I just don't understand.
Yes, you are. So, on that table, what did you use to look up the value on that table?
The letter is in the.
Okay. So,
This is found by the book.
okay, so we used the reference.
Mhm.
But this question is what we were just talking about. What was the value for vapor pressure in the experiment based on? What did you use when you looked up, when you used the book to look it up, or did you use to find your number?
My calculation.
No, you didn't. You used a specific certain thing to pick the right value off of that table. You guys had to do two if I'm not mistaken. Didn't you? Did you have to average two numbers together? No?
Mr. Brown, I don't know. You can't say that and then walk away.
I can, watch. So where'd you get that number?
Is there a way I can see that?
Sure, I'll put it back up there for you. Maybe now you can see what this table is based on. No, that's what you're given over there. What determines which one of those numbers you grabbed?
Mr. Brown.
James, what can I do for you, sir?
So I have a question. About 6 figs.
I figured that. Okay, go ahead.
So my mind brought me to 3 significant figures.
I don't know. What number did you use to find those?
I found them with the mass.
Okay, how many sig figs are in your mass?
Mass.
In your mass?
3 significant figures.
How many?
3.
Really?
Yeah.
You want to check that again?
So was that 2? Because
I'm waiting for you to finish that statement.
3. Because there's a decimal point that's used
Right, but where are the zeros in that number? Beginning, middle, or end?
beginning.
Zeros at the beginning of a number are,
Not
so how many sig figs in that number?
2.
So how many should be in your answer then?
2.
Okay, good. Glad we could have this conversation.
So it'd be 0 moles.
That's not even a sig fig.
Oh wait.
Zeros at the beginning of a number
Oh yeah.
are not significant. I wouldn't start counting sig figs until you hit a non-zero digit. Yes, sir. Well, that depends. What number did you get in number 1? Those look pretty close.
Yeah.
That's good. That means your percent error is going to be very little. Now, your sig figs suck, but other than that, yes. I know it's not right. Okay, so show me your value for number 1. Oh my goodness, where number 1? So 0.00181, where is that in here? Okay, so let's get that on here. What's your number for number 4? How did you get that? Can I see? You use the pressure of water vapor, not the pressure of hydrogen gas. So that's going to make a big difference. That's going to change that number dramatically. And then that will make this percent error a lot different. Okay? Matter of fact, it'll make it probably about 2.25. Okay? Abdi, questions?
Discussion.
What?
Discussion.
Oh, okay, good. All right.
I have a quick question. Can my percent error be negative?
Yes, your percent error could be negative. The main thing is we want your percent error to be near what number? 0. I don't care if it's positive or negative. We want it to be a low number. Good, 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 good. All right, ladies and gentlemen, questions? You got the rest of the day to get this done. And since you're going home early, you got 2 extra hours to spend time on chemistry, working on it, getting it done, getting it turned in. That's an awesome gift for you today, ladies and gentlemen. Awesome gift for you today. Okay, so let's talk about this. We have done P1, V1, T1 equals P2, V2, T2. Combined gas laws. We've done Boyle's. We've done Charles. We've done Gay-Lussac's. We've done Avogadro's. We've even done an ideal gas law. Well, now it's time to talk about some special relationships, ladies and gentlemen. Now, here's the one thing I will tell you, ladies and gentlemen, because I am the most wonderful, generous, and incredible science teacher who teaches chemistry in this building. You can't argue with that either, because I'm the only one who teaches chemistry in this building. I will give you these formulas for your test. I'll put them on there. You don't even have to write them down in your periodic table, ladies and gentlemen. But you better darn well know how to use them. So we're going to start out with something called the law of partial pressures. It says the total pressure in a mixture of gases is equal to the partial pressure of each gas in the mixture. Hey, guess what? We just did that. P total equals the pressure of the hydrogen gas plus the pressure of the, yes, water vapor. Good, excellent, wonderful. Why? All gases have to be at the same temp. All gases have to be occupying the same volume. The moles of the gas can be different, and the pressure of the gases can be different. So, what it means is that the total pressure is equal to the pressure of each different gas in the container. Now, what does etc. mean here? Yes, I don't know how many gases you're going to have. If you only have 2, you only need A and B. If you have 3, you need A, B, and C. If you have 26, you need the whole alphabet. Questions? Good. A mixture of gases has a total pressure of 15.6 psi. Gas A has a pressure of 3.58 psi. Gas B has a pressure of 4.98 psi. What is the partial pressure of gas C? Plug everything into your formula. Total pressure, pressure of A, pressure of B, solving for pressure of C. I don't care what the gases are. We're solving for them. Okay? When we do, ladies and gentlemen, what do we do mathematically to get P, the pressure of gas C alone? We subtract. So we take this 15.6, we subtract 3.58, we subtract 4.98. Questions? So now let's think about a relationship here, ladies and gentlemen. These 3 gases, A, B, and C, make up this total pressure, correct? Which gas is the most, they're the most of?
C.
A, B, or C? Why? Good, good, thank you. We'll stop right there. That's good. We'll just move on. No, come on, give me something more, Andy. I know I cut you off. I'm sorry. I'm a jerk. Go ahead.
Because they don't. If you subtract the 2, or you add them together and then subtract it from the total, it'll be more than both of them.
Okay, and Andy, all you had to do is say it's the largest number. So, considering C generates a majority of the pressure here, right? More than A and more than B. That means there has to be what of gas C? More of it. That's why it's generating more pressure. The only thing that is different about these gases, their volume and their temperature is the same. The only thing that's different is their pressure and amount of gas. And pressure and amount of gas are in what kind of relationship, Michaela? They're in a direct. So if you get more pressure from a gas, it means there must be more of that gas in your container. Questions? Good, because that's our next thing that we're talking about, and it's called mole fraction. Okay? The total number of moles in a mixture of gases is equal to the moles of each gas in a mixture as well. Doesn't that make sense? If I have 1 mole of gas A, 1 mole of gas B, 1 mole of gas C, how many moles of gas do I have? 3. We add them together. By the way, if I have 1 mole of gas A, 1 mole of gas B, 1 mole of gas C, equaling 3 moles total, what would their pressures be compared to each other? Equal. They would all be equal. Why? Because we have the same amount of gases, so they're going to have the same pressure. Good. Way to catch on quickly. Good job. Here's the formula, ladies and gentlemen. The mole total equals the moles of A plus the moles of B plus the moles of C, etc., etc., etc. Doesn't that just look like the last formula? It is, basically. The pressure, the total pressure is made up of the pressure of all the gases. The moles are made up of all of the moles of the gases. Questions? Mixture contains 4.35 moles, 1.12 moles of gas A, 1.25 moles of gas B. How many moles of gas C? Now they call it mole fraction. Why mole fraction? I don't know. I don't know why they don't call it partial moles, but it's this fraction of the moles is this part of the total. You add them together, okay? So 4.35 moles equals 1.21 plus 1.25 plus some mystery number. We solve for the mystery number. It's 1.98. Now, which of these three has the lowest pressure? A, B, or C?
A,
Why?
because it has the least amount of moles.
Good. Which one has the second least amount of pressure? B. Why? Has the second least amount of moles. So how many moles determines how much pressure? Question. Good, because now we're going to use that. A mixture of hydrogen and oxygen gas has a total pressure of 785 millimeters of mercury. If the partial pressure of hydrogen gas is 545 millimeters of mercury, and there are 2.35 moles of hydrogen gas, how many moles of oxygen gas are in the mixture? Can I use the mole fraction formula I just showed you? You got a 50-50 chance.
No,
Why not? You're absolutely correct. Why not?
because they're not all in the same unit.
Okay. And we were never given a total amount of moles. If we were given the total amount of moles, I could use that, correct? The moles of one plus the moles of the other equal the total amount, right? But I'm not given the total amount, am I? What am I given the total amount of? Pressure. And I'm also given the amount of what? Okay, and also the okay. So what I'm going to use, ladies and gentlemen, is called a proportion. I'm going to set up a ratio. The pressure, the portion of pressure that comes from the hydrogen over the total pressure should be equal to the moles of hydrogen over what? So moles of A over mole total should be equal to the pressure of A over pressure total, correct? Does this make sense? Again, if half of the moles are one kind of, or part of the gas, if half of them is the total, what does that mean for the pressure? It's half of the total pressure, right? Okay, well, we know there are 0.235 moles of hydrogen, right? We know there are 545 millimeters of hydrogen gas pressure over the total pressure, correct? So all I can do is solve for mole total here. The moles of hydrogen over the mole total should be equal to the pressure of hydrogen over the total pressure, right? So we would do what here? And then, well, we would isolate this variable, right? Okay, when I do that, ladies and gentlemen, this is what I get for my calculation. Okay? So I got 2.35 times 785 over 545. That will equal the number of moles. Do you trust me on my math? Okay, so what's the total? 3.38. But that isn't what we were looking for, is it? What do we still need to find?
The moles of oxygen.
How do we do that now?
Subtract the moles of hydrogen from the mole total.
Mole total, which I just found, minus the moles of hydrogen will give me the moles of oxygen, correct? Good. Questions? I'm not trying to confuse you here, but I want to show you another way of doing this problem. Now, the reason that I struggled with the moles of oxygen is because I didn't have the mole total, correct? Yes? No? Maybe so? But let me ask you this. Could I do this? What would go up here?
Mole of oxygen.
If there is a relationship between the pressures, there would be the same relationship between the moles, correct? But I can't use this. Why? What? Don't I? How could I get it? So I could take 785 is equal to 545 millimeters of mercury plus the pressure of oxygen. There's another way I could solve this, right? What's the pressure of oxygen? How much? Okay, I'll do it. 240 millimeters of mercury. So 240 millimeters of mercury over 545 millimeters of mercury is equal to the moles of oxygen over what number? Which is 2.35. Now, I am betting, ladies and gentlemen, since we only have 3 minutes left, that if we do this math, what will the moles of oxygen equal? My last class confirmed it for me. So Dante, 240 divided by 545 times 2.35.
1.03.
Works out, ladies and gentlemen. Works out. Okay? This relationship can be between the total moles and the pressure of each mole or pressure of each gas. It can be between two parts that make up the moles. The pressure of one gas over the pressure of another. There are a lot of ways you can use these, ladies and gentlemen. Not just the way they are shown to you in the formulas. Questions? Well, I thank you for your attention today, ladies and gentlemen. I thank you for working hard at the things that we did.